This is an overview of the project about optimization of liquidity allocation in decentralized exchanges. Traditional financial exchanges work through centralized institutions matching the orders of makers and takers. Decentralized exchanges, however, work through a smart contract on a blockchain, managing assets of some investors, letting traders swap assets. Liquidity providers now have an option to choose a price range in which their assets will be swapped, effectively leveraging their liquidity. Decentralized exchange protocols are fairly new and their trading volume matches many established markets. This is particularly the case for Uniswap v3 protocol. Investing in Uniswap v3 as liquidity providers is supposed to turn in fees from trading in the pool. However, research shows that a lot of the investors are incurring loss. This is primarily due to the fact that the liquidity provider's position acquires whatever the market demand gets lower for. Investors need to take into account this among many other factors while deciding for a liquidity allocation range. Decision of liquidity providers is mainly the price range of their position. They can also choose to change this range, with an associated transaction cost. Future value of the position is a very complex stochastic function. Width of the liquidity allocation interval and duration of positions have varying effects on the profitability, introducing conflicting objectives. Decision problem faced by a liquidity provider is formulated in several ways. Some only take into account the liquidity allocation range, while others also consider the future plan of the investor. The most basic optimization problem is to decide for an interval such that the expected return at a known expiration is maximized and its variance minimized. It can be extended to a problem optimizing a capital value associated with a position assuming it is held forever. This value can be modeled as the discounted future cash flows of the position. A more general problem considering time can be to optimize the ultimate value of consecutive investment positions. The best foreseeable plan, assuming the market processes are stationary, repeat positions with same intervals around the last price for the same durations. A more natural problem is concerned with whether the position should be updated at any given time or not. Such a problem is also modeled in this project. These were the decision problems formulated. Every possible decision is simulated for evaluation, before the best among them is selected. The first simulation technique is generating sample price paths using GBM. Empirical distribution of returns can also be used to generate samples, bringing along advantages and some challenges, which were addressed. In contrast to most financial Monte Carlo studies, simulating a liquidity pool's behavior necessitates simulating market volume as well. CAPM is used to select the best solution among those dominating others. Here are some example results. This is an example simulation of the position value distribution, showing effects of the sample number. Here is a comparison of behavior for two different liquidity allocation ranges, alongside a multi-objective comparison with many others. Here is an example evaluation of the distribution of effective interest rate, which is the function of interest for our planning models. Thanks for listening.